Hey there, everybody. Welcome to the second part of section 7.5. Before we dive into this, I want to give you a quick life update. I won in the Battle of the Pants with my son. He is now wearing pants. He is not happy about it, but I have won, and the victory is mine. I should say that small children, though, have a way of turning all victories into Pyrrhic ones. So I won, but at what cost? That's what I say to myself after every battle I win with my children. At what cost? And the cost is usually pretty high. But anyway, you'll be happy to know that my children are all wearing pants. All right, so the goal of today is to visualize using slope fields how systems of differential equations behave, or how their solutions behave. Slope fields were a pretty useful tool back in chapters 1 and 2 to give you a visual of how single DEs, their solutions behaved. So now we're going to use the same kind of tool to look at systems. Okay, so here's a 2x2 system. We have looked at this system many times now in previous videos. So what would a slope field mean here? So notice this 2x2 system, it is two differential equations. And differential equations, among other things, are giving you slope information because derivatives are slopes, right? Derivative tells you what a tangent slope is. Now, though, we're getting sort of a vector of slope information. So notice this first differential equation. What is it saying? It's saying the slope of x1 is whatever x1 is at that time plus whatever x2 is at that time. Okay? So like x1 prime of t, right? So at time 1, what is the slope of x1 at time 1? It's whatever the value of x1 is at time 1 plus whatever the value of x2 is at time 1. So again, remember, everything here depends on time. What's the slope of x2 at time 1 or time whatever? The slope of x2 at that time is 4 times whatever x1 is at that time plus the value of x2 at that time. So for a given time, you can get a slope vector, right? A slope for x1 and then a slope for x2. Two pieces of data giving you a vector, and you can draw a slope field off of that. Let me just show you what that looks like. So GeoGebra draws some pretty nice vector fields. I've sent you, on the Moodle page, there's a link to this. Let me see if I can find Moodle here. Sorry for the mess now, but if you go to the Moodle page, there's now a new section called links. This link right here, link to GeoGebra page that draws slope fields, will take you here. This will give you a slope field of a 2x2 system. The only drawback of this is that it can't handle x1, x2 notation. You have to use x's and y's. So notice x1 plus x2 becomes x plus y. But anyway, that's not too hard of a translation to make. And you get a picture something like this. Now, I think when you guys first do it, notice there are these buttons here. I've already played with these to make this look nice. So for example, if you see something like this, or like this, it can be a mess, So density, the more the density is, the more arrows there are. And of course, the more arrows there are, maybe the harder it is to make out. So if I scale back the density, right, it just does fewer and fewer arrows to make the picture less cluttered. Scale, what does that do? It takes arrows that are long and makes them not as long. So if I do like this, it shortens the arrows. So that also makes the picture less cluttered. You can zoom in and zoom out. Anyway, if you have a cluttered picture, the way to make it less cluttered is to mess with these buttons until you can see things properly. So let me just, I think I'll keep the scale a little bit, but then back the density. Maybe, I don't know. It's hard to make it super uncluttered. I'm going to back off the scale a little bit and make it denser. There you go. So with this, it's still kind of cluttered, but we can see what's happening. So let me just explain what we're looking at here. This is living in x1 and x2 land, or x and y land. That means that this horizontal axis is an x1 axis. This vertical axis is an x2 axis. There is no t-axis in this picture. I want to clarify that, right? That's very important. In this picture, we're watching x1 versus x2. Now, of course, x1 and x2 depend on time, so time is kind of embedded in this picture, but at the very least, this axis down here is an x1 axis, this vertical axis is an x2 axis. So what you're watching with this flow diagram, you are watching how x1 and x2 flow together over time. So for example, suppose that x1 is 1, Right, there's a little 1 down there. Suppose that x2 is 2. That puts you at this point in this flow diagram. If you follow the arrows, you're going to shoot off this way. Okay. Now, what does that mean? It means you're going to move to the right, and moving to the right means that x1 is increasing because this is the x1 axis. If you start here, you're also going to be moving up. What does that mean? That means that x2 is also increasing because x2 is this vertical axis. So if you start here, if x1 is 1 and x2 is also initially 1, you now know from this picture that x1 and x2 will both shoot off to positive infinity. What if you start here? This is like x1 being negative 1.5 or something and x2 being 3. If you start here, notice what happens. You move to the right. You basically flow like this, right? You make a little parabola. You flow to the right, which means x1 is increasing always. You initially, though, flow down, which means initially x2 goes down. But then right around here, x2 ticks back up, and then we just follow up to both of them going to positive infinity. So all that to say, if you have a start value of x1 and x2 in mind, this diagram will show you what the two functions do over time. If your start value is here, right, what happens? Now we move left, so x1 is decreasing. x2 initially ticks up, but then x2 also goes down. So if you start here, both functions will limit to negative infinity as time goes on. So this picture lets you see all that sort of thing. It lets you see what x1 and x2 are doing together over time. I have a screenshot here. I have a screenshot in the slides from your book of the system. Your book, when it draws these slope fields, it makes all the arrows have the same length. The advantage of that is that it just gives you strict flow information. So these arrows over here we've seen from the picture are actually way longer than the arrows here. But if all you care about is the flow, just where things going, it's better to have the arrows have length 1. So I didn't know how to make GeoGebra do that. But anyway, here's the slope field from your book. And again, your book has these labeled. This is an x1 axis, that's an x2 axis. So that's a slope field of a system. Now with this slope field, there are two other visuals that I want to talk about. The first is called a phase portrait. This is a phase portrait. It also, notice, is happening in x1, x2 space. So x1 axis, x2 axis. And what is this picture? This picture is just, in this diagram here, pick your favorite start point. Like imagine starting there. That would be like x1 being a half and x2 being negative 1. And just imagine a line that follows these arrows. So that line or curve, I guess, would go like this, sort of following and then up like that. So you get sort of a hyperbola, parabola kind of shape there, whatever. That's what this is. So pick a start point and then follow the arrows. So a phase portrait is made up of curves like this. These individual curves are called trajectories. So this is a trajectory that starts at the point, 0.8 comma negative 1.2 or something is where it starts. This trajectory here starts at the point like 1.1, negative 2.3 or something. So if x1 starts at 1.2 and x2 starts at negative 2.3 or whatever, then you would expect the two functions to track like this together. Okay, so a phase portrait is just obtained from a slope field by, again, picking a bunch of start points and then drawing curves that follow the arrows. Now the last visual I want to discuss is an actual graph of one of the functions. Okay, so the original system is this. So what we're trying to do are find actual functions, x1 of t and x2 of t. We want to find actual functions of t. T is the independent variable, and x1 is a function of t, as is x2. So in the end, if you want to understand the system, what you would really like are graphs of x1 of t or x2 of t. Okay, so here, notice this is x1 and there's t. So these graphs are living in sort of the normal place where you'd want to draw a graph, right? If x1 is a dependent variable on t, you would like to be able to graph x1 in a place like this. T is the horizontal axis and x1 the vertical axis. So what this is showing you here are these trajectories that have been sort of pulled apart into x1 and x2 pieces to get these plots. Okay, so just think about this trajectory here. This trajectory starts when x1 is 2 and x2 is negative 3 or something, whatever. Let's think about what happens to x1 as you travel along this curve. What happens to x1? Well, initially this curve goes to the left a little bit, doesn't it? This curve goes to the left a little bit. What does that mean? That means that x1 is decreasing a little bit because movement towards the left means x1 is going down. Okay, so notice if I start at 2 here along that trajectory, initially x1 goes down a little bit. Right? This curve bows to the left a little bit, but then it sort of turns around and starts moving to the right. And moving to the right means that x1 is increasing. So that's why you see this curve take off like this. Let's think about this trajectory here. This guy here. What's happening along there to x1? Well, initially, x1 is starting at like 1.8 or something, whatever. There's like a 1.8 right there. So I'm starting at like 1.8, and then again, the trajectory moves to the left a little bit. So moving to the left a little bit means that x1 is going down. But then it starts moving back towards the right, right about here, right? It starts moving back to the right, meaning x1 is increasing, so off it goes. x1 increases off to positive infinity. Okay, well, what about like this trajectory here? What about something like that? Well, along that, what's happening? x1 is just going down the whole time. This sort of trajectory here, or this one or whatever, right? If you think about what x1 is doing over time there, x1 is just going down, right? This is the leftward movement corresponding to x1 decreasing. So that's why these curves are just going down. So anyway, if you want to know what x1 itself is doing over time, right, what you have to do is pick these trajectories and then ask yourself, what is x1 doing as I travel along here? And again, x1 goes up if you're moving to the right, x2 goes down if you're moving to the left. You could also, of course, plot x2 graphs if you wanted to. To plot x2 graphs, though, x2, right, as this trajectory moves, you're asking whether you're going up or down, not left or right, because x2 is the vertical axis. So in a trajectory like this, x2 just goes up, right? x2 starts at -1 and then just builds up to negative infinity. A trajectory like this, though, x2 starts at like 2.3 or something, goes down to 2, and then x2 turns around and goes up to positive infinity. Whereas a trajectory like this, x1 starts at -1, and then x1 just continues to build to positive infinity because this trajectory moves rightward. This trajectory is always moving right, whereas this trajectory is moving down at first and then up. Okay, so all that to say, here are the visuals that you need to think about a system like this. A slope field itself lets you think about how are these solutions flowing together over time. So again, depending on where you start in this diagram, the two solutions either both go to positive infinity or both go to negative infinity. This phase portrait allows you to sort of draw paths through that slope field and flow with the arrows, right? And then these individual trajectories allow you to finally get what you really wanted, which was to understand x1 as a function or x2 as a function. You can plot those graphs. Okay. Also, these sort of pictures, there's language surrounding them, the kind of picture they are. In this kind of slope field I just looked at, this is called a saddle. It makes these sort of like saddle shapes here, you know, kind of like in Calc 3, getting a saddle point. So what happens here, there's a dominant eigenvector and a non-dominant one. So this system here, we've solved it before, we've analyzed it before. There are two eigenvalues. The eigenvalues are -1 and 3. Okay? 3 is bigger than -1. Okay, it's not controversial. So what happens is, when I say dominant eigenvector, non-dominant eigenvector, the dominant eigenvector is the one associated with the larger of the two eigenvalues. So since 3 is bigger than -1, the eigenvector family for 3 is dominant. And we've analyzed this before in this system here. The eigenvector for 3 looks like 1, 2. So look in this diagram, 1, 2. Right, there's where that vector would be, 1, 2. So in this, watch, 1, 2. See this blue line? That's that family of eigenvectors. Right, here's 1, 2, and then any scalar multiple of it. And notice all the trajectories are flowing towards that dominant eigenvector. Now the eigenvalue of -1 also has a family of eigenvectors. That family is -1, 2. -1, 2. So those eigenvectors form this blue line. And notice this blue line is like a repeller or something, right? So all the trajectories flow away from the non-dominant eigenvector and they flow towards the attracting eigenvector line here. That's called a saddle. So anyway, you can give language to the kinds of pictures you will see. And the reason, by the way, we'll come back to this in Chapter 9. We need this language a lot in Chapter 9. The reason you get a picture like this is because the eigenvalue of 3 is positive. The eigenvalue of -1 is negative. When you get a sign mismatch like that, one positive, one negative, you get a picture like this. Okay, so your exercise for this video is to get a slope field of the following system. So you should do that in GeoGebra, and then draw yourself a phase portrait and sketch some plots of x1. You could also sketch some plots of x2 if you want to for practice. So pause the video and see if you can do that. Okay, so assuming you're back, you've gotten a slope field. It should look something like this from GeoGebra. You may have had to approximate square root of 2, or you may have typed in square root of 2, whatever. But here is the slope field you get here. Looks like a magnetic field or something, okay? Here's what a phase portrait looks like if you follow the arrows from different start points. And then something like x1. What is it doing over time? Okay, so let's think about right here. What is x1 doing if you start right there? Well, these arrows are flowing leftward, aren't they? So if you follow the arrows, x1 just dies to 0. What if you start over here? These arrows are flowing rightward. So also going to 0, right? These are negative values that increase now to 0. So you get pictures like this. Okay, so the origin is like a sink here. Everything is flowing to the origin. And how are they getting to the origin, by the way? Notice, they're being sucked in by an eigenvector line, just like in the previous example. Okay, so if you ask Wolfram for the eigenvalues and eigenvectors of this system, the two eigenvalues are -4 and -1. -1 is bigger than -4. Its eigenvector will be dominant. Its eigenvector, again, if you ask Wolfram, is √2/2, 1. And that's what this line is here. √2/2, 1 is that vector extended to infinity. So that vector, again, is acting like a sink. And this vector here, though, now notice, it's no longer acting like a repeller so much. That doesn't look like a saddle, really, right? This dominant guy here, right, just kind of sucks everything in, and then everything goes towards the origin. It's not so much a saddle anymore, though, right? It's sort of different looking than this. In this picture, this eigenvector is sort of a sink, but this less dominant one is like a repeller, right? You don't see something quite like that here. It's a little different. So anyway, there's language surrounding this. The origin, in this case, is called a node. There's a dominant eigenvector and a non-dominant one, and now just the dominant one just sucks everything in. The non-dominant one isn't really repelling things. And again, the dominant eigenvector is the vector associated with the larger of the two eigenvalues. That's how you could have predicted. That's how you could have predicted this blue line here, and how you could have predicted the sucking in at that line, right? This blue line is the attractor, not this other one. This line here, again, corresponds to the smaller of the two eigenvalues in this system, and that smaller value is -4. This line here was the eigenvector line corresponding to -1, the bigger of the two eigenvalues. Okay, so to conclude this, we'll be looking at slope fields for systems as we move through the material. They just give you a nice visual of what's happening over time, right? So again, this kind of picture doesn't let you solve the system per se, just like slope fields back in Chapter 2 didn't solve anything for us. But just like back in Chapter 2, these pictures let you see sort of the big picture. Over time, what are these solutions doing? And like here, over time, we can see they are dying to 0. Both functions together die towards 0 here. Whereas in the other picture, we knew that both solutions together either went to infinity together or went to -infinity together. You can make predictions like that by looking at these pictures without even having to solve the system. Okay, so in the next video, we'll turn to section 7.6, which is dealing with 2x2 systems, but whose eigenvalues are complex instead of real.